Alright, hi and welcome. Today we'll be talking about sigma notation in the nth term. Okay, sigma notation is just basically this notation right here. Pretty simple, straightforward stuff. Okay, your first term that you're going to plug in is 1, all the way up to whatever k is, you're going to plug it in. And this would be actually your nth term. Okay, your formula that you plug in here. So this is actually called the index of summation. So this is actually kind of cool. And what it means is you're going to take all the terms of the sequence and add them up. Okay, now n factorial is n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. So whatever the number is, you start at that number, then go to the next number, and you just times all the way down. Okay, so working with this stuff, you guys, you can write it out you can actually do it two ways. Method one is to write it out. So, like for example, we are working with this. Okay, all right, so you write it out like this. All right, so once again, this is a series. This is sigma notation. Okay, this is our index of summation. We start at the first term and we go up to the 7th term. Okay, and here's our pattern inducer. Okay, so what you can actually do is you can write it out and just calculate it simply as that. So the first one would be 1 cubed minus 4, and then you add that with 2 cubed minus 4, and then you add that with 3 cubed minus 4, all the way up to 7 cubed minus 4. Okay, and you would just sum that all the way up. Now also you can do this on your TI-89 calculator, and here's the actual notation that you would plug in. So this would be let me see, the sum, and then you press sequence inside of it, and then you're going to have your n cubed minus 4 parentheses. Okay, so you have your formula, then you have the n, that's your variable. Okay, and your starting value is going to be 1. You go up to 7, and you do it by 1 step each. Okay, and you plug that into your calculator and you just work with it as is. Okay, if I use my calculator real fast, I can tell you that's going to be 756. Now you could seriously write it out and just add it up like that. That's totally fine. But I highly recommend finding a calculator that can do this really fast so you can actually work with it. Now what you could also do is you could seriously just use if you knew that this was an arithmetic sequence, you could actually use an arithmetic series to actually find this. But we don't know that this is arithmetic sequence because guess what? This is definitely not a constant between these two, okay? Alright. Alright, so if we take a look at this and we write this as, okay, this is n equals 1, okay, that's the first term, this is n equals 2, this is n equals 3, and this is n equals 4. We don't know what this is actually going up to as it works with it. But if you notice something unique about it, wait, if you try to compare it to squares, it actually starts to make more sense. Because guess what? This is 4 squared minus 1. This one's 5 squared minus 1. This one's 6 squared minus 1. This one's 7 squared minus 1. This would be 12 squared minus 1. Okay? Alright? So, what we could do is we could actually shift all of this, and we don't have to have this summation index right down here. We could actually start this at 4. Okay, and this is 5, 6, and 7. It's like, oh, and go all the way up to 12. Okay, so when we write out our actual term, okay, we could write out the sum of all the terms. Now it's just basically n squared minus 1, so we could write it out as n squared, squared minus 1. Okay, and you could actually just re-represent it as this. So some really cool stuff to actually work with there. Okay, alright, let's take a look at one more turning into a sigma notation, and then we'll move on. Alright, so if we start this as n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. Just work our way up. If you notice, the top part of the fraction is actually going to be 2 times that number. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, all of that. So the top part of my fraction, let me write it out. So this is actually going to have a 2 times n on the top. Okay. All right, now on the bottom, it's going to be awfully hard to see that, but if we take a look at the actual factorials, 2 factorial is 2. 3 factorial is actually going to be 6. And 4 factorial, if you notice, this is actually getting to be kind of creepy. That's 4 times 6, so that's 24. Okay? If you notice, that kind of lines up with this. So this is just one more than what we need. Okay, so we'll be adding 1 to each one of these n's as we go. Okay, so we will go n plus 1 factorial on the bottom. Okay, and that's the helpful thing about knowing your factorials, is they help you notice some patterns really fast too. Now, if you notice, it is alternating between plus, minus, plus, minus, plus, minus. So I'm going to show you how to write that out. Okay, so when you want to alternate between that, you're going to be raising 1 to the power. So we're going to be raising it to the, now this is going to be tricky, n plus 1 right there, and I'm going to move it over a little bit because it's kind of covering it up. I'm going to have to move it up here, just pretend it's all down there. Well, actually, let's just move this over, let's move this over. Let's get rid of that. Okay, there we go now. Now we can multiply those two. Okay. Alright, now, why did I do -1 to the n plus 1 power? Well, if I did -1 to the n power, this first term should be negative. But it's not, it's positive. Then the second term technically should be positive, but it's actually negative. So it's almost like I'm doing an even power here, an odd power of -1, even, odd, even, you know, and just so on and so on. So that's why I did the n plus 1 to represent the n power. Now, as you work with this stuff, you need to make sure that you take your time and test it out and just work with it. And obviously, since I'm kind of coming up with a problem, I know that it's going to work, and do n equals 1. Now, if I wanted to start this at n equals 2, just work my way across, I would just change this to a 2. I would change this to a, I guess, 6. Yeah, 6 right there. Okay, I would change this to just an n because I wouldn't need the power there. Okay, and this one right here I just changed to an n factorial. But I would need to change this 2n to a 2 times n plus 1, or n minus 1. There we go. So if you do change one of the variables, you do need to change around the rest. So as you can see, I can represent this 2 different ways. Okay. All right, that's it for sigma notation and summations. I'll talk to you later. Bye.